Gas phase kinetics?
Yeah, it is more adequate description. Once I was representing his research in public and told like Dr. Herberger burns everything, and someone told him, and next time he was representing, he said, I do not burn everything. But it is combustion reactions, and then we will partially cover it in the course. Some the molecules have not only color in sense of UV visible spectra, they also have oscillations, the IR spectrum, which is different for different molecules. He is looking. Oh, we already read. Or I'm clapping not because I'm excited about myself. I'm looking for the green stuff that goes on so we can analyze outcome of reaction and see which products are developing. It's not my primary goal, but as time goes by, I may cover a couple of options. Can I ask? Yeah, it's important to make sure that the camera is projected onto one of the screens, or maybe as a subset in the main screen, so that we can focus on. I don't know if you are watching, or anyone is watching this recording, but maybe one day you'll decide that you need it. So, anyone wants to arrange early turn in, or everyone is fine with Monday submission homework one? Okay, Monday. First and last time to submit homework number one. And in a week from now, next Friday, there will be time for another homework. I hate them. I know that it is not the reason for us to come here, but through attempting to solve them, we are getting more hands-on experience in practical approach to the concept that we are going over. And the homeworks, I'm trying to keep some level of challenge. Do not be surprised if it looks not easy. It is intended to be so. Oh, sure. So what is in this homework is material which is complementary to what we do in class. Is there a way to focus it on practice? Focus camera on practice.
Yeah.
So through the material that we have already started, and I will try to help us to recall the general idea of where we are and what are we doing, but we will face a mathematical problem. If you remember the third way to predict future, we need to find expansion coefficient C sub k, right? So projections, we will, and it is not only one time in this class or this chapter, it will be repeated again through semester. So we need to expand our chosen initial condition in the basis of the eigenstate of Schrödinger equation. So we need to multiply the functions and break over the whole space from plus to minus infinity. Right? So this thing is okay. I can do it. Now you can smile and show some signs there. Or turn to the camera and say like, oh. So the procedure of multiplying these two functions and finding integral is kind of boring mathematically, but it is something that we will need to do again and again. So the the problem number 3 in this homework is practice of this thing. So this is challenging. This will take longer. And it is not, well, you can find answer in online, in Wikipedia, in some textbooks. It is pretty standard problem, or even in the chart that I distribute. But if you want to get it without any help, it is a problem that can be solved much quicker through several bypasses. And I'm going to disclose these bypasses as we go through lecture material today, next week. So the problems are not just blindly integrated. There are some tricks that make life easier. Question number 2 is really simple. We'll cover it in 2 days, I guarantee you. And number 1 has almost no relation to class. It is more exercise for the following reason. It provides background for this operation of finding expansion coefficients. So this mathematical problem of finding expansion coefficients of one function over some basis set is known in the history of human civilization as Fourier transform. So most developments of today's math that we use for quantum theory were done by mathematicians approximately at the time of French Revolution. And the stuff that you are studying in differential equations and calculus has some names of the people who were living a little earlier or a little after. So Fourier is one of them, and it is expansion of arbitrary function in the basis of oscillating sines and cosines. So number 1 and number 2 can be done without tricks, plainly. Number 3 needs tricks. So stuff before this time are recorded of what we did in this year and after what we did in previous years. So you are able to submit this on Monday, right? You've got ideas how to do. And here's what I shouldn't show it on this bigger on the bigger screen. So on account of homework, everyone in class got German money. I became lazier this year, therefore I printed it together. Previous years I was just printing it like fake money and distributing. And C, here the C sub A, it is the stuff that we need in our protocol for predicting future. And we will, so here is where I want us to stop. I'm not sure that we will have time for it, but it is good intentions. So we are trying to predict future of electron in the universe where nothing else exists, right? Initially localized. And suppose that we already know the eigen functions, energies, and exponential functions. We will hopefully get through it during the class. And then we need just to get the answer for the future, where the past and eigenstates are stored here. So, by the way, this is the answer for problem number 3 in the homework number 2. So it is the answer that everyone has to obtain. So you already know the answer, but the past. The answer is already known. And this is the integral of getting the future that we will formulate during today's meeting. On Monday, we will try to take. And this is very similar in its nature to what you have to do in problem number 3. So the trick that hopefully we will introduce that this complicated thing, which makes me scared just because I do not like integration, especially complicated functions. But you see, there are exponentials everywhere, e. Not that I have a speech defect, it is just 3 exponential. And we can merge them together and observe that 2 of these powers are square, quadratic, and 1 is linear. And we can reshuffle it and represent as exponential with quadratic and linear terms with some coefficients. And this shape is much easier to practically integrate, where those are okay. So I will try to squeeze, if possible, squeeze in 2 lectures in one because we didn't complete material assigned for last meeting. Kinetic energy in terms of momentum. Kinetic energy is E squared over 2m. Anyone wants to object this equation? No. Then please try to remember it anytime it is required, because the Department of Chemistry was very close to expel one of the graduate students who was not able to reproduce this equation by request. It's considered too simple and necessary to reproduce. So, what is momentum? Momentum operator. Minus I h bar ddx, right? We discussed. By applying it to exponential, you get value of momentum to the front. And it shows density of fringes. Dense fringes means high momentum, sparse fringes mean low momentum. Now we are just plugging in the same as you introduced in the postulates of quantum mechanics. If you take classical variable p and replace it by quantum operator p, then you will formulate the Hamiltonian. And you know, we are in a free space, so that we do not have any potential. The Hamiltonian consists only of kinetic energy. So we take minus I squared h bar squared, then d dx after another ddx. So it will be just second derivative divided by 2n. So Hamiltonian equals I squared will be minus 1, minus 1 squared will be 1. So minus goes to the front, minus h bar squared over 2m d2 over dx squared. So if someone asks you what is the quantum operator of kinetic energy, you just reproduce this equation. Right now you solve for it. Just plug in the definition of kinetic operator in the classical equation for kinetic energy. Good. What is next? Next is that by our protocol of predicting future. Our non-wet chemistry protocol has 3 components that we need to mix together. Eigenfunctions of Hamiltonian for this problem, eigenenergies of Hamiltonian for this problem, and expansion coefficients. Okay? So for eigenfunctions and eigenenergies, we just solve time-independent Schrödinger equation. Unknown energy, unknown. Right? So here under Hamiltonian we use whatever was in the previous slide. And we will, most of the times in the class, we will try to avoid any mathematical challenges wherever possible. So if you were, I don't know how you were taking differential equations. I know some of you were taking it, what your instructor was telling. But when I was taken as the sophomore year, my instructor was telling like a very legitimate way to solve the differential equation is just to guess the solution and prove that it is correct. So if through the experience you have some ideas what can work, which function can satisfy equation, you do not need to torture yourself and try to solve it. There is a good chance that it will be fine. So can we try phi of x in x, just in the functional form that we already played with? So let's guess, let's try that, this trial function, plug it in and check whether this function will or will not satisfy the eigenstate problem, the time-independent Schrödinger equation. Okay, what do I do? Plug it in. Let's see what happens. One change first in dx. Probably I have prepared another slide with spaces to write that. Yes. So we are applying this Hamiltonian to this function, and we are practicing derivatives. So first find first derivative, second find second derivative. We keep whatever is up front changed. And here, when we practice the derivative, it means that whatever was a factor in front of the independent variable comes. This region doesn't respond to handwriting well. 1, 2, and now we apply second derivative to just continue. Apply second derivative. Minus h bar squared to m. The constants I minus ik come to the front, and one more derivative is applied again to minus ikx. You already see and kind of predict the answer. So the exponential is a favorite function of all times and nations because why? Because differentiation doesn't change functional form of exponential, and integration doesn't change functional form of exponential. So it is intentionally designed to match these two operations. So if you take the second derivative, you just accumulate same factor as it was, now in power 2. Okay, squared e minus I. So -1 squared will be +1. I squared will be -1. And -1 again. So
I have a quick question.
please.
Kind of like, is that e to the negative I kx?
Yes.
Okay.
Factors. 1 minus, then -1 squared, and I squared. It should be -1. Minus, plus, minus. Overall sign should be plus, right? Now, h r times k squared divided by 2m times e times I t. So wave number inverse wavelength is related to momentum. Right? So in some sense, here you have p squared, right? So wherever you see h times k squared, you can replace it by p squared. So h I equals plus over 2m times, and you see this function is equivalent to the function of this type. So our unitary operator acting on the plane wave function didn't change the function, which means plane wave function is an eigenstate of this Hamiltonian, right? Probably you will write it down. So it's one observation. Plane wave function is an eigenfunction of Hamiltonian. Another observation. So the function isn't changed, and here pops up what should play the role of eigenenergy. So we can tell that E sub k equals p squared over 2m, or in if we want to pursue the notation of k, h bar squared, k squared over 2m. So by now we have found the, what did we found? Yes, we could. There were arrangements. So what did we found?
The
Eigenfunction and eigenenergy. So before we were only speculating theoretically that while solving time-independent Schrödinger equation, one needs to find eigenenergies. Now we found one. So energy corresponding to this function, eigenenergy, will be this h bar squared k squared over 2m. So nothing cheesy. We found this equation, this function, and this energies satisfy Schrödinger equation, right? Now we are going to use these findings, these components, to form our prediction of future. We will plug them in. And the only thing we are missing is this C of K that we're going to guess very soon. Right. So here is a pattern to predict future. So we make summation over eigenfunctions, and you do know our eigenfunction, it is a plane wave, times exponential with oscillatory factor, where time is proportional, time is multiplied by the eigen energy, eigenfunction, eigenenergy, and then we do not know yet the expansion coefficient, but as soon as we plug it in, our part will be ready to cook. So I will comment on solution of your homework number 2, problem 3. So there you will assume, or we all are assuming, that proton is stolen, that shape of the semi-localized electron has Gaussian shape, okay? We assume that our past at time 0 we have this shape of minus or square or some width parameter. And by now you have accompanied each other, we all as a class found that plane wave, this exponential, this linear in K, is an eigenfunction of the Hamiltonian for this free space. Therefore, if you need to find expansion coefficients, we need to multiply these two functions, Gaussian times plane wave, and integrate over x. So minus infinity to plus. So it is what you are going to do in your homework 2, problem number 3. So upon integration over x, you get function that depends on k, on the wave vector, right? So x will disappear. You will integrate over it. The result will depend on k and on sigma. And the meaning of the answer that you're going to get is very important. So I'm going to concentrate. You may consider taking notes if I will tell something reasonable. So the initial condition, this Gaussian shape, can be represented as summation of plane waves with different weight coefficients. So oscillating waves with different wavelengths. But each of these plane waves will enter into the function, Gaussian function, with different weight coefficients. So we take a little bit of slowly oscillating plane wave, a little bit of quickly oscillating, and then we need certain weight coefficient for each of these exponentials. If you do it this way, then we represent our Gaussian function as summation of plane waves. Try to store it in your own words, and I'm happy to answer.
So are you saying it's like when you have grades and you have like tests are weighted more, each plane wave is weighted differently like that?
Yes.
Okay.
Yes, that's right. So if you have different values of k, and here are the coefficients c sub k, plane waves of each value of k will different amount, different weight into overall representation of our initial function. And there will be a great surprise if when you will complete this assignment, that you'll find that in the c sub k as function of k will also have Gaussian shape. So for k vector equals plus infinity or minus infinity, it will be 0. So this is answer that I am borrowing from the future. I trust that you will solve it, and I'm kind of taking your answer that you will get in 1 week and plugging into our narration today. So those are expansion coefficients of the chosen initial condition over eigenstates of Hamiltonian. Good? No big objections. No small objections. Good. We are about to end last lecture and coming to actual today's. We choose the Gaussian shape. Here is how we represent it in K-space. And now we are going to plug in this C sub k into our prescription for predicting future. Yes, here. We are going to predict future of an electron that originally has Gaussian shape. We already converted the initial condition from coordinate to just function of k. So each term in this equation depends on k, on the wave vector. K squared, k, and summation. So if Schrödinger didn't lie to us, then by taking the summation, we will predict future of an electron. And we will answer our scientific questions that we discussed last time, like whether the wave packet is going to change its width this time, whether it is going to move forward, or maybe do something else. So right now, we do not have. Yes, please.
In the blue box, what's
Yes.
after H bar?
There is no H bar. I apologize for my outstandingly high quality calligraphy. So this is Greek letter pi.
Oh.
This is square root. This is Greek letter sigma.
Thank you.
Yes.
Where did the equation in the green box come from, the e to the negative it over h bar?
Excellent, legitimate question. And it is also perfect. Well, I will tell you later, I will try any opportunity to avoid any exam. If it would be exam, it is a perfect question to answer in writing by text. You will be a great teacher designing right exams. So, you know that wave function depends on both position and time. And we practice separation of variables. So wave function that depends both on position and times can be represented as product of time part and space-time. So time part always has this shape e minus e to the minus I. Some eigenenergy. So by solving time-dependent Schrödinger equation, one is getting this time dependence.
Yeah.
And if you have doubts in dimensions, if you want some non-mathematical argument to believe it, the dimension of Planck constant is energy times time. It's action. Or velocity, momentum times position. So this energy times time can be its equivalent in dimensionality to action. And dividing action by Planck constant, you get dimensionless phase accumulation. I don't know if it makes things more complicated, but for me it sounds very convincing.
Okay, I just didn't know where you had the e to the negative it over the h bar, where it just came from. But
Well, this h bar comes from it is already present in Schrödinger equation.
I just meant the general exponential, where it came from. But you answered it, so.
No small objections, no big objections. Let's go forward. So we just need to take this summation mathematically. Go forward with it. If the functions are mathematically well defined, and the amount of terms in summation is infinitely large, it is completely legitimate to replace summation by integration, just because integration procedure is developed a little bit better. So wherever you have summation of infinite number of terms, this parameter value offset from each other by small number, you can replace this summation. So summation can be replaced by integration. Okay? Oh, okay. Let's do a surprise quiz. So write down your name and fill in the boxes. I guarantee everyone will do it.
Can we use our notes?
Huh?
Can we use the notes?
I didn't warn you to flip it over, so it's too late. Use anything you like. Then it will be a motivation to take notes next time if you were not. So just in case I already noticed some common mistakes, the eigenenergy for each plane wave will be different, and it will depend on the wave vector. The higher momentum, higher the wave vector, more dense fringes, the higher the energy. Okay? This is what I've been thinking. The same initial condition. Which goes to imagine.
This semester, or semester after all of us too. Okay. When do you think the most likely time to be?
Yeah. This, if this one is something more complicated.
Okay.
Yeah, thanks so much for being brave and not running away from the class. Announcement this surprise quiz. So some of you wrote just C sub k into here, which is if you were not taking notes, that's the only way to see. I do not remember these expressions myself, so it's something like square root of pi sigma sub 0 e to the power minus k squared times sigma, something like this. This is stuff that you are going to get in your homeworks. Eigenenergy is h bar k squared over 2m. So everyone was successful in this. And this is just our plane wave, e minus I kx, right? So no one failed on the first two boxes. And this was just a question of memory. So you perform really well. I'm happy. This year is a strong. Okay. I've forgotten. I will implement it next year. One can call one of the people to the blackboard and write it. Okay, I think we are completing this stuff. So we just formulated the problem to no. Do you want to obey the schedule and depart as needed, or you're okay if I give you something additional? Let's vote if one wants who wants to leave immediately. One?
Sorry.
Sweet. Okay, then we postpone this stuff to the Monday meeting. So what is not included today is how to take Gaussian integrals. This is a very nice part of math that I think we need to learn here in class to feel independence in next homeworks. But this is the last slide that we discussed, right? So future will be composed as integration according to the equation that you have already confirmed that you are well familiar with. Meeting is dismissed. Have a nice weekend. See you on Monday. See you and your homework number 1.
We got our homework done. Can we turn it in today, or do we have to wait till Monday?
You can turn it today. You can slide it under my door. You can send it as an email in a format scan. So complete flexibility. Just do not hunt me in front of my own house. Here's my homework.
No, whatever. Monday. Put that. See you Monday.
See you.
So do you really want to show like if someone wants to see the video and you want to show them that, where are you pointing on the screen then?
Yes.
Because there are two different feeds, and one is you and one is the slides.
I'm uploading both feeds.
Yeah, so you still want to like.
I'm uploading both with real video and just screen capture.
Okay. Yeah, I was confused at the beginning. Like, I don't know what you want to show.
So you major in engineering.
Yes.
Which of engineering? I know that
Electrical
okay.
engineering. I don't know. I like this stuff. Probably don't need it.